Dewayne VanHoozer if you like what I have to say. If not, it's Larry Ellison. But before we get started, I need to do a little bit of a demographic here. So if you would please self-identify how many of you are radical terrorists, members of LUSEC, or anonymous? Anybody? How about theoretical physicists? Okay, so I have a requirement. I have to give a joke at the beginning of everything. So the bartender says, we don't serve faster than light neutrinos in here. A neutrino pops into a bar. All right, okay. So good. It's just not my delivery. It's, you know, there's not that many physicists here, but that's okay. I got it. All right. So I like to get an image in my mind about the topic that I want to talk about, and my image is the Minuteman. This is a statue of the Minuteman from Concord, Massachusetts. And the reason I have in my mind the Minuteman is because of the definition of what a Minuteman was. They were able to do things very rapidly. They were able to change from plowing the field to shooting the British. Any British here? Okay. Good. So that was it. They were agile before agile was cool. And so that leads me into basically the topic is rapid prototyping and concept development using Ruby, but not just anywhere here. I am the Senior Staff System Engineer at the Virtual Reality Systems and Integration Lab for Lockheed Martin Missiles and Fire Control. So earlier we were talking about who came the farthest. So who here works for a company with over 70,000 people? Oh, okay. So I guess I win. I have some things that I want to show you that you've never seen before. And if you never see me again, that's probably because I'm showing you things that you've never seen before. So the first thing I want to show you is what we do in the Versal. The very first video doesn't have any Ruby at all involved. But I wanted to show it to you anyway, because it brings a message. That was a video we produced in our lab. And no Ruby was involved. No Ruby involved, dinosaurs. Sounded like the perfect message to bring. Now, the second video is actually going to be kind of a demo reel of a bunch of things. And this demo reel took over 1 year to get through the approval process to actually make available to the public. And we made it available to the public about 6 months ago. It's on YouTube. If you go to YouTube and search for Lockheed Versal, this is what you'll see. Ruby was involved in the production of this. virtual reality systems integration lab. We are an incubator inside of a large corporation, and there's about 9 of us in this one lab. We have 2 graphic artist engineers. We have a facilities manager, a military operations analyst, and then the rest of us are software engineers. Majority of us have over 25 years of experience in doing software engineering kinds of stuff, but we also bring in college interns and help mentor them. So we're not only incubating new ideas and new products, but we're also incubating new engineers into the company. So within the lab, we have 2 tools, 2 tool sets. We have the integrated system environment, and then we also have the EVE, the engineering visualization environment. And what I'm going to be talking about today is the integrated system engineering environment, ICE. ICE is a Ruby product. And this is why we built ICE in the first place, because within a large enterprise like Lockheed, within a large customer base that has many different things, we have this kind of architecture. We have individual kingdoms that have been around for years. These are our legacy systems. When they were developed with the concept that nobody else in the world needs to know anything about what we have within them. Yesterday, one of the presentations referred to these as walled gardens. And so we needed some kind of a system that would help us integrate and allow the different walled gardens, the kingdoms, to interoperate with each other. And so that's when we came up with ICE, the Integrated System Environment. Now, this is what happens. Let's pretend that we have 3 kingdoms. We have the dog kingdom, we have the cat kingdom, and then the rest of us represent the other kingdom. And in terms of communication protocols, we can't talk to each other. So what we need is something that sits in between each one of the kingdoms, like the United Nations Translation Service. Now, I'm told that these windows back here in the back, these are not corporate hospitality suites. They're supposed to be the translators are back there. So everybody at the UN hears in their own language and their own protocol, but other people are speaking in different languages. So ICE is like that. ICE sits in between the kingdoms. And so when the dogs go woof, the cats hear meow. When the cats purr, the dogs hear grr, and simultaneously to that, this is what we hear. Okay? So, that's ICE. ICE is approximately 142,000 lines of Ruby code. That makes up about 80% of ICE. Now, whenever a programmer starts talking about lines of code, he's probably lying, just like whenever a politician moves his lips. So, what does that mean in reality? Well, I used a utility called schlock count that actually compared it, and it turns out that it's about the same size in terms of Ruby code as we find an active record and AREL together. Now, a couple of things about ICE that I wanted to show. This is a graph produced by Stats SVN. We use Subversion for our source code control. And early on, we were doing branches based upon developers. So every developer had a branch. And it just didn't work. After about 6 months, we threw that away, and we said all the developers are going to be working in the same branch. And we called that branch the edge branch. And when we did that, we just had a much better time of it. Vertical bars are when our feature branches are brought back into our main edge trunk. So we had an audit last May about the Versal and specifically about ICE. And that audit determined that ICE was responsible for over 8 figures worth of new business brought into the company. And that's 8 figures to the left of the decimal point. So ICE has really shown itself to be a very lucrative piece of work. We actually were expecting to go to 9 figures at the end of the summer, but there's been contracts that have been pushed into next year. So our backlog is not as high this year as we were expecting. And of course, I only had to say 8 figures here because it's one of the things that I couldn't tell you was exactly how much money the lab was making. I'm sorry. ICE basically enables us to develop simulations and interoperate between these different legacy systems. One of our largest simulations is an air and missile defense simulation. It's all Ruby, the entire simulation. So what I wanted to show you here is that as we were prototyping, we were able to get, can you see this red line from the back? Okay. 6 months into our program, we got to the point where we were feature complete. The principal investigator who asked us to create a prototype said, all right, that's wonderful. Now I'm ready to bring in customers. So we started seeing generals and other people come through our lab. And they thought, hey, that's really wonderful. Can it do this? Can it do that? Well, we say, yes, of course we can. And then the principal investigator said, okay, now would you build me a prototype to do that? Well, it turns out the architecture that I had put in place was not adequate to do the kinds of things that we wanted to do that our customers said that they would like to see. So we had to refactor. That's refactoring, almost starting over. So basically I had to throw out a bunch of code. Don't be afraid to throw away your code. Because after we refactored, we were able to bring in a bunch of the code based upon the new architecture and new features and sell this thing off. This is going to account for a large part of that 8 figures. And it's all because we were able to go to the customer without a PowerPoint slide, but with an active, actual product prototype and say, this is the way we think it ought to work. And the customer said, you're absolutely right. Here's $1 billion, go build me one. This is a medium-size simulation that we developed. This one I can talk about a little bit more. Again, you'll see major points of refactoring. This one is what's called a microgrid. It's for power management and power distribution. We completely did all of the control work and developed all of the optimization techniques in Ruby. And the customer really liked it. And the customer said, okay, go build me some. And this is one of our small simulations. We've been talking about mocking and other stuff. This simulation is actually, the lab was given the task of being the true witness between 2 competing interfaces, the hardware design team and the software design team. And so we said, hey, we can help you out. And so we wrote the interface control document for them. But we went more than that. We said, here is our simulation of what the hardware is going to do, and here's our simulation of what the software is going to do in terms of the interface, based upon the document that we wrote. And then we could give the software side to the hardware guys, and then we could give the hardware side to the software guys, and they could develop in parallel. And they would verify their code against our simulations. So this is how ICE works. We have a central database where we store stuff, and then we have a distributed file system. So our database stores things like job configurations, services that are available on our network. And our shared file system contains executables, libraries, and other stuff that we want available throughout our cluster. We have what we call the peer. The peer is the mainline logic that controls basically just the main, if you would think in terms of C or anything else. But it's what loads in the different libraries and models and stuff. And we actually have 3 peers. Peer D was the very first one we developed. It was developed in C++. Then peer RB is our Ruby peer. It does exactly the same thing peer D does. And peer J is our Java peer. It does exactly the same thing the other 3 do. So we developed kind of a pattern that says we have a defined API, we have a convention in terms of class naming and method naming, and then we have the peers. And so what we have are simulations that are running that are a mixture of C++, Java, as well as Ruby. The peers load up what we call models. Models encapsulate the business logic of the thing it is that we're trying to simulate or emulate. And that can span the range of a macro mega model that just says, hey, I'm going to have all the business logic of a battlefield. Or it can be a small model that says, I'm going to have all of the business logic necessary to move a fin on a rocket. So models span the gambit. But the models are loaded by the peers. And so their API is associated with the peer, and that's how the peer knows how to call the model, to tell the model to initialize, for example, or tell the model how to shut down. So it's when you combine these 2 things together that you actually get an executable. And peers can actually load up multiple models here. That's what I'm trying to show. Now, we have a job configuration language, which is written in Ruby. And that job configuration goes out to the database and says, okay, the user wants to run this particular job. And that job consists of all of these different models. And so the system then takes those models and flings them out onto our network. This represents, hey, 2 real computers. One of them might be attached to our hardware integration lab devices. The other one might be a high-performance computer. And those little things up there at the top reference or represent virtual instances of a situation. So this would be one job running across 2 real computers and 4 virtual machines. We use VMware quite a bit, and VirtualBox just happens to be my favorite. Now you noticed the concept of ICE router. When we first started talking within the company about ICE and how it works, I mentioned the ICE router, and I got blank stares back. Nobody that I was talking to knew what routers were. Now, I think we all get the concept of what an ICE router is, but it wasn't until I actually showed this picture to some of the senior staff and said, this is what routers do. They route messages. Some of them didn't quite get it, and I had to give them another example, just so that I wasn't being chauvinist. There's all of these messages on the table, and the router routes the messages to the right place. And so after I showed them that 2 things, they finally got it. They said, oh, an ICE router routes messages. Yeah. One of the very first ICE routers that was developed we called the dispatcher. The dispatcher was written in C++, and it's what handles all of our military protocols, such as Link 16, Link 11, Link 22, Tattle J. We also are simulation protocols, HLA, DIS, CMD, all alphabet soup, I'm guessing, in terms of, unless you're in the military. So this would be consistent with routing binary by wire or XML messages and converting them from one format to another. And we use the same kind of a plug-in process where we can plug in different methods for getting the information to the different models, either by pipes, by sockets, or by shared memory. We also have the concept of the filter and the transformation, so that we can filter messages based upon a model's subscription. It says, hey, I want to receive this kind of message, but I only want to receive it when it's within my geographic area. Or transform it that says, hey, I want to receive this kind of a message, but please change it for me so that it was produced as big indent, for example, but I want to see it as little indent. The second ICE router that we put together is based upon AMQP, and I just want to say RabbitMQ rocks. It's one of the best little products that I've seen out there. RabbitMQ, we pushed over several million messages per minute against RabbitMQ in one instance, and the thing is popped. It just does a marvelous job every time. Our key concept is the pattern that we developed. And basically, we hide the complexity from the developers, and we only expose the API. Now, this is not that new, but within the business group that I was in, this turned out to be exceptionally well received. You notice that was an iceberg. But we also have the concept of the smart message. Now, the smart message is a message that knows how to do things to itself, knows how to publish itself, knows how to subscribe to itself, log itself. And this turned out to be a tremendous savings in terms of time. This is what some of that code might look like. This is a message. Now, I know everybody here knows Ruby. Anybody not know Ruby? Okay. When I showed this kind of code to people who have only been doing embedded C++ or Ada code, they went berserk. You mean you can do things like that? It is just remarkable. Now, actually, it was this code. They said, wait a minute, don't you have some kind of syntax? And I said, yeah. So you can publish a message and take all the defaults, or you can publish a message and tell that publication process what router you want to use, what kind of router, what kind of encoding technique. You can even tell it which logger to use if you wanted to. Those C++ guys just kind of stared at me. This is the way we subscribe to messages. We tell the message class we want to subscribe, and then we give it the callback method. Or maybe I went the wrong way. No, there it is, sorry. So that's the subscription. Some of the lessons that we've learned. But it's more than that, Albert. You can't rely upon people's brains. You know why? Because they're people's brains. So you can't rely upon remembering that you need to do a backup. Let the computer remember. Let the computer do all of the automated backups for you. We actually had one guy on a different project outside the lab, never backed up his system, never used the source code repository, never did any kind of versioning control, and guess what happened when his computer crashed? 6 months worth of company intellectual property went out the door, could not be recovered. Guess who else went out the door? So, automated backups. Manage the configuration. And that's more than the source code. We already talked about it in the session prior. You got to manage the configuration of the machines that you're working on as well. And we do that primarily the way that we discovered that was the easiest way to manage that configuration was with the virtual machines. So we can create one virtual machine and then deploy it several places. no programmer's an island, right? No problem is too hard to be solved if you use the team. Because every one of us has some kind of a specialty. We have certain skills that nobody else has, and when you bring everybody together, you can solve just about any problem. This solved a lot of problems for us. We originally started with cruise control about 4 years ago, and we only used cruise control on our Ruby products. But one of the things I didn't mention is that we never deploy any Ruby products outside of our lab because all of our products are rapid prototypes or concept development, proof of concepts. Our deployment process deploys with a different platform with either Java or C++. But by bringing in the continuous integration process, one of the things that we were able to solve was the conflict problem. Because you commit often, you test often, you communicate all the time. And communication is the key. That's the key component of Agile. If you have some kind of a silly Agile process in place that says you've got to do this on Monday and you got to do this on Friday, that's not as effective as just talking to the person who sits next to you. Talking and communication is the important thing. Our continuous integration process, I said we started with cruise control about 4 years ago. This year, we have done no Ruby products in the lab because we are actually deploying, we've already taken our prototypes that we've developed and we're now deploying them in Java and C++. In January of this year, we moved to Hudson. And Larry, being Larry, pissed off more people, and Hudson forked. So when we took a look at what was going on with Jenkins in March of this year, we said, hey, Jenkins is moving along faster. They're solving more of the problems that we're having, so what we're going to do is we're going to switch over to Jenkins. So we've been using Jenkins since March. And Jenkins has turned out well for us. It works on our Ruby products. It works on our Java products. It works on our C++ products. It runs all of our regression tests. Every time we get a successful commit, all of our tests are successful. One of the things that we do with Jenkins is we actually tag that particular revision. And so for QA, we always have within our Subversion repository a tagged item that says, this revision has passed all of our regression tests. If you've got two people and they have two different ideas about what the product is going to be, they're not going to work well together. So one of the key things is to have a shared vision. You have to know up front within the development team exactly what the goal is, when we're going to try to get there. You have to have that shared vision. If you don't have a shared vision, you're going to have too many conflicts. But being developers, even if we do have a shared vision, there's going to be conflicts in terms of technology. Well, I want to do something one way. Why? Well, I never did that before, so I want to try it out. Well, that's okay. So long as you have that shared vision and you know where you're going and what time you need to get there. This is one of the most important lessons that we learned. Time is relative. It's almost like the pay me now or pay me later kind of thing. Don't be afraid to throw away your code and refactor. Sometimes it may actually take a week out of your schedule. Okay? You may say, I've got this entire week, and instead of doing the next feature, what I'm going to do is I'm going to refactor the previous feature. And it turns out more often than not that simple thing of taking a week, sometimes as long as a month, to refactor your base, to refactor your architecture, actually saves you time in the end, and saving time means saving money, right? That's the other thing we learned. There was not one task that we gave Ruby that it couldn't do. Well, now, okay, I take that back. When we took some of our cluster-based simulations and the client said, hey, remember that little 6-month thing where we dropped down to 0? the client, in our case, it was the principal investigator, said, hey, I want to put a road show together, and I want to take this simulation on the road and show it to people. I need it to all work on one little laptop. Okay, so we had this supercluster where we were running the simulation, and things were kicking and just doing wonderful. And then we put it onto a laptop, and guess what? Its performance slowed down significantly, so that was one of the reasons why we had to do the refactoring. But what I'm saying about Ruby is even with performance, if you've got the horsepower in terms of iron, you just change your algorithm a little bit, and Ruby takes care of it. Because who's more expensive, me or the computer, right? We are. And did I mention backups? Backups. It's plural. We back up daily from one server to another server. We back up weekly from our main server to a network-based system where that network is also backed up. And we also back up to removable media that we take off-site. So one backup by itself is not necessarily sufficient. And what do you call a backup that's never been tested? A failure, exactly right. You should always, whenever you do a backup, the very first thing you should do after taking that backup is to do a restore and make sure everything works. Because a backup that's not tested is a failure. In this particular case, this warhead builder is management. Who can blow you up more than anybody else? Management. Never surprise management. If you're going to be late, tell management as early as you know. If you're 3 months out from a deadline and you know it's going to take an extra month after that in order to get something done, tell management. Even though the risk is something that they can handle it. They also like to know if you're 3 months out and you're going to be done in another month. They want to know that too. So never surprise management. Always let them know what's going on. Now you're looking at the board over here, right? And you're saying, hey, that's the design. And this is what was delivered. That's wrong. This was the design. This was the prototype. It was from the prototype, from the proof of concept, that the design was derived. So don't be afraid to do prototyping, because you will get a much better design if you prototype. And when things work exactly the way you expect them to work, celebrate. I told you earlier that we never deployed Ruby outside of the lab. Well, that's not entirely true. We had one group come by, a group that saw our prototypes. They said, that solves a problem that we have right now. Would you please let us use your prototypes? And we said, well, we would be happy to let you use our prototypes. However, your regulations say that you cannot deploy Ruby in this fashion. So they went through higher headquarters and they got written permission that allowed them to deploy our prototype. And that gave us an extra contract for not only building the real thing, but also supporting the prototype in the field. So that's all I had to say.